I would like to start by introducing myself. I am Stallone. I did my 4th year at FETS last year, electrical engineering. I love microprocessors. Since 2020, the year that I did my 2nd year, I never stopped engaging with microprocessors. I did dozens of projects using different kinds of assembly language, ranging from 8051 assembly language, 86 assembly language, ASM assembly language, AVR assembly language, PIC assembly language, and many more. Enough about myself. Now let's look at what we have here. You are doing microprocessors, right? But you are going to be working with a microcontroller. What are the differences between a microprocessor and a microcontroller? The major difference is that a microprocessor is designed to be the processing unit of a computer, and the major components that it needs for it to perform its tasks, they are external. For example, the memory that it uses is external. Peripherals like timers, clocks are external. For a microcontroller, all those major components, they are built in. So the microcontroller that you are going to be using is the PIC16F18446. Whenever you think of a microcontroller, think of it as a small artificial brain that is various components which perform various functions. What are the computations that the microcontroller is capable of performing? We are going to look into those in depth. For example, it can perform addition, it can perform multiplication, subtraction, and so on. Peripherals. What are peripherals? These are just additional components that the microcontroller has to help it perform tasks that are crucial to us as programmers. Programming. We are going to look at how we can program the microcontroller. Different kinds of programming languages that you can use. The one that you are going to use is PIC assembly language. We are going to look into it in depth. The course in general. What are the components of the course? We are going to look at how you will maximize from each component so that your overall mark is a distinction. The microcontroller is capable of performing binary arithmetic, binary addition, binary subtraction, binary multiplication, binary division. It is capable of doing that with integers and decimals, known as floating point numbers or fixed point numbers. The microcontroller can also perform logic operations. You might have heard of AND, NOT, OR, NOR, XOR, and so on. It can perform all those logic operations. We are going to look at those in depth when we cover digital logic. Lecture 1 from week 1 that you were given by Dr. Chabalala, it looks into the basics of those. But how does the microcontroller perform these computations? It performs them by executing the instructions that are given to it through programming. We are going to look at that in depth. For each instruction execution, there is fetch, decode, and execute, and a repetition of that results into successful instruction execution. The guy who is responsible for these computations is the arithmetic logic unit. All of these computations, the binary arithmetic and the binary logic, they happen in the arithmetic logic unit. We are going to look into this in depth when we cover the architecture of the microcontroller, or in simple words, when we cover the components that make up the microcontroller. Now let's look at the peripherals of the microcontroller. The peripherals are additional components that the microcontroller has that helps it to perform tasks that are crucial to us. There are digital peripherals that include timers, PWM in full pulse width modulation, and serial communication peripherals such as SPI, the serial protocol interface, UART, 12C. In one of your labs, you are going to use SPI. Timers, this peripheral, we make use of it when we want delays. Let's say in one of our programs, we want the microcontroller to delay for a certain period of time before doing another task. Let's say, for example, we want the microcontroller to turn an LED on and off, on and off, over and over again. So that period when the LED is on and that period when the LED is off, that period can be provided by timers. So the professional ways to achieve delays in assembly language is to use timers. There are what are called active delay loops. We will look into those, but the use of timers is considered a professional way. There are analog peripherals. The major analog peripheral is the analog to digital converter, which is known in short as ADC. This one is used to convert from analog values to digital values. For example, let's say we want the microprocessor to read the temperature of our environment. The analog values are produced by the temperature sensor. Those values are voltages. Let's say for a specific temperature, the output of the temperature sensor is 0.32 volts. So that's the analog value. So this analog to digital converter, it converts that analog value to a digital value. So for example, 0.32 volts analog can be converted to a corresponding digital value of, let's say, for example, 13. ADC, timers, and PWM. These peripherals are very important, and you are going to use them for your projects. We will look at each one of them. We will look at them in depth as the course progresses. The pulse width modulation peripheral can be used to divide digital voltage. By digital voltage, I mean, let's take for example, you turn on a lamp, you turn it off. Turning it on a lamp requires a digital voltage of, let's say, for example, 5 volts, and turning off 0 volts. So if we want to divide the digital voltage, we can make use of pulse width modulation. Digital voltage, you can think of it as DC voltage, and analog voltage, you can think of it as alternating voltage. Now let's move to programming. So to program this guy right here, you guys are required to use assembly language, PIC assembly language. Of course, you can program it using C or C++, but this course requires you to program it using PIC assembly language. The first thing that you will need is the instruction set manual. You need to make sure that this guy is always by your side. I have an example right here. This is the instruction set manual from the datasheet. I think it's from page 602 or 604 if I still remember well. I will share with you the one that I made, and I advise that you print it out so that you are always with it. I even suggest that you put it beside your pillow when you sleep. It is about 50 instructions. I only took a snapshot of the last 2. The trace instruction and the XOR WF instruction. This instruction set manual, you need to print it out. It's either you can extract the one from the datasheet, or you can print out the one that I'm going to share with you, the one that I made already. We are going to look into how the memory of the microcontroller you are working with is organized. This is very important for you to know. The memory of the microcontroller includes what are called registers. And we have 4-bit registers, 8-bit registers, and 16-bit registers. Registers are just memory sections with bins known as bits. 8-bit registers have 8 memory bins, with each bin capable of accommodating 1 bit, a 0 or a 1. When we cover the memory organization of the microcontroller you are working with, we will see that the memory is grouped into banks, memory banks. Bank 0, bank 1. If I remember well, the PIC16F18446 microcontroller, it has more than 2 banks. That is very important to know, because these registers that we discussed about earlier, for you to make use of them, you need to switch to the right bank first. Looking at this code, we can see that we have a bank cell TRISC-A. With this directive bank cell, we are first switching to the bank that the register TRISC-A is in, before we can make use of TRISC-A register. Another thing that is very important to focus on is the Curiosity Nano. Let me say the chip itself, its pinout. You will get this from Veronica. This is our guy right here, the microprocessor. Our guy is right here. This board is just an extension that makes it easier for us to make use of this guy. These are the pins of the chip connected through this board. It's very important to know all these pins. For example, here we have pins for port A, pins for port C. We will cover those in depth when we do I/O ports. So it's very important to know all these pins, because each pin here has a corresponding bit, and each port has a corresponding register. For example, here you can see we are saying bank cell port A. So a port is just a collection of physical pins, right? If you look at the chip itself, you will see that it will have these pins, right? These are the physical pins. Right. MOSI, so all of these pins are for SPI communication. We are going to look at this in depth. We are going to cover all of this till you know these pins by heart. This is a simple example of the exam-like questions that we are going to be looking at. So what this code does, it reads values from port A and port C, 32 on port A, 76 on port C, and add those values together. And use indirect addressing, it asks the final value of 37H, and 37H is a general purpose register. While we are on memory, there are what are called general purpose registers, special function registers, configuration registers, and so on. We are going to look at those in depth as the course progresses. Here are more examples of the exam-like questions that we are always going to be looking at. These questions will help you to know assembly language in and out. With all the questions that we are going to cover, it will be very easier for you to do the project on your own. Of course, I'm going to have your back on the project, but you will do it on your own. And if Miss Alice makes a mistake of asking questions like this in the exam or tests, you will wreck all of them. Now, let's look at the course in general. The course has 4 components: labs, the project, tests, and the exam. For the labs, it's very important for you to know what you are doing and what you are supposed to do. We are going to cover them together, and it's very important for you to know everything that you are supposed to do. These labs are very important because they will form a preparation foundation for the project. All the sessions that we are going to cover doing code exploration questions like the ones that we saw earlier are going to be preparing us for the project. And the project, we are going to work on it as soon as the brief is released. The tests that you are going to have are going to have two components, the programming part and the digital logic part. The programming part will be asking about the chip and the programming side. The digital logic will cover binary arithmetic and the logic, which comprises of combinational logic and sequential logic. Combinational logic cover basic logic gates like AND, OR, NOT, and advanced logic gates, which is a combination of these basic logic gates like K-maps, half adders, full adders, and so on. Sequential logic will cover finite state machines, flip-flops, and so on. We are going to cover all of that way before tests, so that you are prepared for these tests way before writing them. The exam will have the same format as the tests. Right. I want all of you guys to get at least 70%, but this is only achievable if you guys cooperate. By cooperation, I mean, if we agree that we are having a meeting, you should not miss it. Or if we agree that I'm going to make a short, detailed, high-quality video, you will watch it as soon as I release it to you. And also, if I give you some questions for you to try, you should try your best to do them. This is the kind of cooperation that I mean. If you cooperate like this, there is a high guarantee that you are going to get at least 70%. If you cooperate like this and get less than 70%, I am willing to refund you. Okay, guys? So this was all for this session. For the next session, we are going to start looking at the chip, its memory organization, the components that it have, its pinout, and we are also going to explore the instruction set manual and cover some basic instructions and use them to write some simple programs.